This would be the penultimate class of the course transport phenomena. So, what I would continue to do to explain some of the problems on momentum integral equation, because I thought that is a portion which I could cover in greater details, especially in the form of solved examples. So, this would again be a tutorial class on momentum integral equation. The specific problem which we are going to solve in this class is about flow in a horizontal duct. So, a duct is formed by two parallel plates and air starts to flow in the duct, and the ducts are well rounded. So, that it is going to start as a laminar boundary layer, but as it grows it will become turbulent, and we know what is the thickness of the boundary layer at some distance into the duct. So, the geometry of the duct is horizontal. We have flow of air in the horizontal duct, and there are two stations 1 and 2. One is right at the mouth of the duct, at which point the flow is uniform. That means, the velocity is not a function of distance between the ducts, the velocity is uniform across the cross section. But at location 2, since the boundary layer has formed on both the top plate of the duct and the bottom plate of the duct, the velocity at the free stream would definitely has to be higher than the velocity which we have at the beginning, because at the beginning the flow was uniform, but towards the end, I mean, if you look at the picture, I think it would be more clear to you. So, this is the picture that we have for the duct. So, what we have here is the air outside far from the duct is obviously still air. So, it does not have any velocity, and the pressure at that point is equal to 1 atmosphere. And this duct, which has been it is a horizontal duct, initially at location 1 at the entry point of the duct, the velocity is uniform and equal to 10 meter per second. When I come to point 2, location 2, at a distance of 5 meter, from 1, the thickness of the boundary layer both at the bottom, and we are going to have similar boundary layer at the top. This thickness delta 2 is equal to 100 millimeter. The separation between the plates, the dimension is h equals 300 millimeter. So, we have a system in which we have a duct, two stations, thickness of the boundary layer at location 2 is known to us, the separation between the two plates forming the duct is known, and we can take any width of the duct, it really does not matter. So, we can call this as width W. So, that is the width of the duct. The problem, if I can read the problem once again for you, is that the flow of air whose density is provided develops in a flat horizontal duct following a well rounded entrance section. The duct height h is 300 millimeter. Turbulent boundary layer grows on the duct walls, but the flow is not fully developed. So, that means the two boundary layers have started forming on from the entrance up to that point, but these two boundary layers haven't touched each other. So, therefore, the flow is still developing. In this region the flow is inviscid, but inside the boundary layers the flow is still viscous, it is still two dimensional flow. It is a function of x as well as it is a function of y. It has been mentioned that the velocity profile in the boundary layer is given by the 1/7 power law equation, which you are aware of. The inlet flow is uniform at 10 meter per second, as I explained before. At section 2, the boundary layer thickness is delta 2 equals 100 millimeter. So, the first part of the problem, which we also have done in the last class, is we have to show that the displacement thickness delta star is equal to delta by 8. Then the next part is we have to calculate what is the static gauge pressure at section 2. What is the pressure at section 2? That means, we would like to know what is the value of P2, and this is P1, and outside it is P0 to be equal to 1 atmosphere. And third part of the problem is find the average wall shear stress between location 1 and location 2. okay, and the region outside it's still air with velocity equal to 0 and pressure equal to 1 atmosphere. So, we will start solving this problem in this class, and I think it would give you more ideas about the use of momentum integral equation and how the body forces, the surface forces including shear are connected to the convective transport of momentum because of the flow into the control volume that we are going to define into the boundary layers. So, the first is starting with 1/7 power law, we have to show that the displacement thickness is equal to delta the thickness of the boundary layer at that given location divided by 8. So, that is the first part of our problem. So, we will quickly start the problem then. By definition, the thickness delta star is the displacement thickness is 0 to delta 1 minus small u by capital U, where capital U is the free stream velocity times dy, dy being the distance from the solid plate. So, if I take delta outside, the limit changes. So, it is going to be 1 minus u by capital U times d eta, where eta is simply y by delta. So, the limit will change from delta to 1. This u by u, this follows this is the 1/7 power law. If it follows 1/7 power law, then delta star can be written as delta times 0 to 1 minus eta to the power 1 by 7, that is the 1/7 power law times d eta. So, when you perform this integration, it would simply be eta minus 7 eta to the power 8 by 7, within it varies between 0 to 1. When you perform this, you are going to see that delta star is equal to delta by 8. So, this part is straightforward, which we have done in the last class as well. So, when we next is, so this is part 1 where we have to show this. Part 2, it simply tells us find the what is the static gauge pressure P2. So, this is the static gauge pressure at 2, and it has been mentioned that P0 is 1 atmosphere outside of the duct, but we do not know what is P1 and what is P2. So, the gauge pressure here would be equal to 0, and we need to see what are the gauge pressure at these points. So, the first thing we need to do is we need to find out what is the velocity at location 2. So, we need to find out what is the velocity at this point, because if we know the velocity at this point, only then I can write the Bernoulli's equation between 1 and 2, because this core is in inviscid flow, and boundary and Bernoulli's equation is only valid for inviscid flow. So, therefore, I know the velocity at this point. So, if I can find out what is going to be the free stream velocity at this point, which is going to be affected by the growth of boundary layers over here. So, then we should be able to apply Bernoulli's equation between these 2 points. So, the first one that I am going to from continuity, I can write V1 A1 is equal to V1 times area is W, which is the width, constant width times H. So, at V1 at 1, the entire area is under the velocity V1, under the constant entry velocity V1. So, this is going to be my V1 A1, and at location 2, the velocity outside the boundary layer, let us call it as V2, but the available area utilizing the definition of the displacement thickness would be equal to H minus 2 delta. So, in order to convert the flow situation at location 2 to an inviscid flow, what needs to be done by the definition of delta 2 star, by the definition of displacement thickness, is to raise the platform by delta 2 star, which would make the flow outside of this to be inviscid. So, if I can raise the platform at this location by a distance equal to delta 2 star from both sides, then in this region the flow is going to be inviscid. So, the flow is going to be inviscid in this region. So, I need, so this delta 2, this much, this is delta 2 star, the displacement thickness. So, by definition the solid boundary here has to be raised by delta 2, and whatever be the velocity at this point, essentially the entire fluid will be in inviscid flow if I constrict the flow area by a distance equal to h minus 2 delta 2 star. So, that is what I have written over here. In order to have this free stream velocity, I raise the platform on both sides of the duct by an amount by a distance equal to delta star. So, my inviscid flow area now has become h minus 2 delta star, and W, the width, is definitely constant. So, I should be able to obtain what is the value of V 2. V 2 should be equals V 1 h by h minus 2 delta 2 star, and for delta 2 star I use this condition. So, delta 2 star would simply be equal to delta 2 divided by 8. Okay. So, this V 1 would simply be 10 meter per second, and the h is 300 millimeters, and 300, this h 300 minus 2 delta 2 star by 8. So, this is delta star by 8, this is delta by 8. So, delta at this location is provided to be equals 100 millimeters. So, delta 2 star would simply divided by 8. So, delta 2 star is evaluated as delta 2 divided by 8. The value of delta 2 is 100 meters. So, divided by 8, and this would give you the velocity, the free stream velocity, if I assume the flow to be inviscid, to be equals 10.9 meter per second. So, using the simple definition of displacement thickness, I find out what is the velocity in the duct at location 2 if the entire flow is inviscid. And in order to convert viscous flow to inviscid flow, I use the definition of the displacement thickness. So, at displacement thickness at point 2, location 2, is simply the distance by which the two ducts will have to be brought closer to each other, such that the entire flow now becomes inviscid flow. And the moment it becomes inviscid, then I can apply Bernoulli's equation between point 1 and point 2 across any streamline, so to say. So, between point 0, which is outside of the duct, and point 1, between outside of the duct, which is point 0, and location 2. Since the entire flow starting from this point, the point 0, all the way up to 2 is now inviscid flow, I can write Bernoulli's equation between these 2 points. So, that is what I am going to do next. So, the Bernoulli's equation would simply tell you that between the outside, which is where the pressure is P 0, atmospheric pressure, by rho plus V 0 square by 2 is equal to some pressure inside the duct plus whatever be the velocity at that point divided by 2. So, this P could very well be P 1 or P 2, and the corresponding velocities are V 1 and V 2, all in inviscid flow. I also realize that since the air outside of the duct is still air, so my V naught is equal to 0, and therefore, the pressure, let us say of location 1, if I express in gauge pressure, which would simply be whatever be the pressure at 1 minus P naught, where P naught is the atmospheric pressure, So, if P naught is the atmospheric pressure, then P naught P1 minus P0 is the gauge pressure, which would simply be equal to, if I write this equation between location 0 and location 1, or I can write it for location 2 as well. So, if I write it for location 1, then P1 minus P0, which is the gauge pressure, would simply be equal to minus half rho V1 square, which after you put the values of rho, and this P1g would turn out to be minus 61.5 Pascal. So, the negative sign in gauge pressure simply tells you that the pressure at 1 has to be less than the pressure at 0, which is obvious, which is intuitive, because unless the pressure here is less than the pressure outside, there will not be any flow through the duct. So, what you have to, so some external agency must have created a suction towards the other end of the duct, which simply draws the air into the duct. So, the pressure at this point would be less than P0, which is atmospheric pressure. Since the pressure at 1 is less than atmospheric pressure, so therefore, the gauge pressure is going to be negative. And if we move towards point 2, the gauge pressure would be even more negative. So, that is what we are going to do next. So, my P2g would simply be equals P2 minus P naught, P naught being the atmospheric pressure, minus half rho V2 square. We have already calculated what is the value of V2, which is 10.9 whole square. So, your P2g would be equal to minus 73.1 Pascal. So, these two pressures, these two gauge pressures would simply be used to work the next part of the problem. So, the part 2 is also complete. We know what is the static gauge pressure at section 2 as well as section 1. The next one is we have to find what is the average wall shear stress between 1 and 2. In order to do that, what I am going to do is I understand the flow is symmetric across this axis. The flow over this half and this half are symmetric. So, I am going to draw my control volume in one half of this and write the momentum integral equation and see if I can find out what is the average wall shear stress. So, my control volume, the one which I am going to use for my analysis, is the, let us say, the lower half of the duct area. So, it is lower half of the duct area. I have momentum coming in by convection, momentum going out by convection. There is a difference in pressure between this point and this point, and some wall shear stress is acting on the control volume. So, the wall shear stress is acting on the control volume in the reverse direction, reverse to that of the flow direction. The pressure difference forces the liquid to move from this side to this side. So, the two surface forces which are acting are due to pressure difference and due to shear. Since the duct is horizontal, there is no body force and you have convective transport of momentum and convective momentum out of the system. So, now I am going to write the momentum integral equation for this half of the duct and then see if I can find out what is the tau wall shear stress exerted, a wall shear stress that is exerted over here. So, now we can move to part 3, and in order to solve part 3, I apply momentum integral equation using half of the duct as the CV, control volume. So, the momentum integral equation, the x component of momentum integral equation is f s x, the surface force in the x direction, plus f b x, body force in the x direction, is equal to del del t of control volume, u the velocity, rho d volume, plus over the control surface, u the local velocity, rho v dot dA. So, rho v dot dA is simply the mass flow rate which is either coming into the control volume or going out of the control volume. And according to the convention that we have used, if you recall, mass coming into the control volume is always taken to be negative, and the mass which is leaving the control volume will be positive, because the mass flow rate, if you see, it is the dot product of the velocity vector and the area vector. The last one, the area vector, always point normally outwards of a surface. So, clearly you can see that when V and A are directed oppositely, then you are going to have negative. So, flow into the control volume is always negative, flow out of the control volume is positive. So, with this and with our understanding that there is no body force acting on it and we are working at a steady state, so there is not going to be any accumulation of momentum inside the control volume. The surface forces must be balanced by the net transport of convective momentum into the system. First surface force, you are going to have a pressure force and you are also going to have shear which is acting on the control volume. The first pressure is P1 minus P2, these are the gauge pressures multiplied by the area, and since I am using half of the duct, so the area is simply going to be W times H by 2. And if wall shear stress, average wall shear stress is tau bar, so therefore, the force exerted due to shear on the control volume would be equal to minus tau bar, because wall shear stress is exerted on the wall. So, therefore, the wall is going to exert a force equal but opposite direction, equal but in opposite direction, opposing the flow, and that is why we have this minus sign. It is working on an area W times L, where W is the width and L is the length. So, the area for pressure, you can clearly see the area on which the pressure force is acting is this area, which has area equal to whatever be the width multiplied by H by 2, whereas wall shear is acting on L times W. So, these are the two different the two areas are therefore different, and then this is going to be equal to V1 bar at this location. V1 bar is the velocity. So, the momentum would be mass times the velocity, mass rate in times the velocity. So, it is V1 is the velocity, and since the flow is in, it is going to be rho V1 bar times H by 2 into W. So, this is the area multiplied by the velocity gives you the volumetric flow rate. Volumetric flow rate multiplied by the density would give you the mass flow rate. Since it is mass in, that is why it is going to be negative. And the last part, the second part can be thought of as consisting of two parts. One is A and let us say this is B. So, if I draw the situation at location 2, up to this point I have a boundary layer, and this is my central line, this is the line of symmetry, the plane of symmetry is this line. So, this is A, where the flow is through the boundary layer, and this is B, where the flow is through the inviscid region. So, the flow at 2 can be thought of as if it is consisting of two separate layers. In one I have viscous flow, in the other I have inviscid flow. So, A and B both will consist if I find out what is the momentum that goes out through A and B, then I know what is the total momentum which is going out of 2. Therefore, the amount which passes through A is 0 to delta 2 u rho u w dy. Note two things is that u is a function of y in the A region, therefore, I am using the integral sign and I know that my thickness of my A is up to delta 2. So, this part integration of rho u w dy, this is the mass flow rate which leaves the control volume. Since it leaves the control volume, it is plus, and it is to be multiplied with the velocity, with the local velocity, and integrated from 0 to delta 2 to obtain the rate of momentum which goes out of the control volume because of the flow. So, since it goes out, it is going to be positive, and then for B, I know that the velocity is going to be equal to V2 because that is the inviscid flow. So, the velocity here is equal to V2, and this is to be this, and I find out rho, the mass flow rate as rho V2 h by 2 minus delta 2. So, this total distance is h by 2, and I subtract delta 2 from there. So, this is the region through which inviscid flow takes place. This multiplied by V times W. So, this is the area, total area of B, of the region B, h by 2 minus delta 2 multiplied by whatever be the constant width, multiplied by V2 would multiplied by V2 would give me the volumetric flow rate through region B, multiply by rho would give me the mass flow rate through region 2, and I multiply it with the velocity again in order to obtain what is the momentum that goes out of this part of the control volume. So, this is for part A, region A, and this is for region B. In one case I have viscous flow, the velocity is a function of y, that is why I need to integrate. In region B, the velocity is a constant, area is constricted h by 2 minus delta 2, and in both cases momentum is going out, mass is going out of the system, that is why they are going to be plus. So, if this is your governing equation which gives you the average value of tau in here. So, let us separately work out what is going to be the value of A and that of B. So, if I find out A, if I am finding out A, so which is 0 to delta 2 u rho u w dy. So, this would simply be equal to, if I divide it by V2 square, it is going to be 0 to delta 2 u by V times rho u by V times w dy. Now, all these are at location 2 corresponding to. So, this is essentially u2 by V2, and I can, instead of y, I can write eta to be y by delta. So, if I do that, my integration sign changes from 0 to 1, and the final expression for this would be rho V2 square, sorry, this is V2 square times delta 2 times w 0 to 1, and what you have is then u2 by V2 whole square. That is what you have in here. Since it is following 1/7 power law, u2 by V2 is simply going to be eta. So, u2 by V, u by V at location 2, square of that would simply be equals eta to the power 2 by 7. So, eta to the power 2 by 7 times d eta. So, when you perform the integration, it is going to be rho V2 square 7 by 9 delta 2 times w. One more time, what I have done here is I have divided the flow at location 2 as if consisting of two subflows. The part A, which I have denoted, this through the part A viscous flow is taking place, through part B inviscid flow is taking place. If it is inviscid flow, then finding out the mass flow rate is simple. Just multiply the constant velocity V2 with the area. What is the area? The one that is remaining after you subtract delta 2 from the total h by 2. So, the area through which inviscid flow takes place is h by 2 minus delta 2, the whole thing multiplied by the constant width w. Multiply that with the constant velocity V2, you get the volumetric flow rate. Multiply this volumetric flow rate with rho, the density, and you get the mass flow rate. This mass flow rate is to be multiplied by velocity V2 again in order to obtain what is the momentum flow rate, what is the flow out of the control volume by convection. Next is you are going to find out the momentum flow out of the control volume in the region A, where viscous forces are important and where the velocity in the x direction is a function of y, is an indeterminate function of y, or it is a function of y that we are saying that it is going to follow 1/7 power law. So, therefore, since it is not a constant velocity, in order to obtain the flow rate out of the region A, I need to integrate. So, what I have done is in A I have integrated from 0 to delta 2 u rho u dy, and then by substituting the 1/7 power law in here, I calculate what is the expression for momentum flow out of the system of A. So, therefore, the expression that I have here, I am going to find out what is tau WL. It's simply going to be, if I bring it to the other side, tau WL would simply be equal to the pressure force P1 minus P2 W h by 2 plus rho V1 square h by 2 times W, which is the flow rate through region B, and then rho V2 square h by 2 minus 2 by 9 delta 2 times W. So, this essentially gives me the average value of the wall shear stress, which is tau, and therefore, tau would simply be equals 1 by L P1 minus P2 times W h by 2 plus rho V1 square h by 2 times W minus rho V2 square h by 2 minus 2 by 9 delta 2, and I have another W in here. So, this is the total complete expression, and once you put in the numbers for P1, P2, W, h by 2, V1, V2 and delta 2, what you are going to get is tau bar is equal to 0.3 Newton per meter square. So, important point in this specific problem is that you are finding out the average value of the wall shear stress, not the point value of wall shear stress. So, you may ask that I have a profile at location 2 which follows 1/7 power law. So, why not differentiate the profile at 2, multiply it with mu and obtain what is the value of the shear stress? You would be wrong, because you have been asked to calculate what is the average shear stress between location 1 and location 2 over this entire 5 meter long region, not at point 2. So, do not try to use the expression to obtain an average value based on the velocity profile which is there at a given location. So, I hope that this problem has this solution tutorial problem has clarified any remaining doubts that you may have on the use of momentum integral equation. If you still have some questions, please ask me, and I will try to answer to you as soon as possible.